Hello, welcome to our video on soil description and soil classification according to World Reference Base for Soil Resources WRB, 4th edition 2022, edited by the International Union of Soil Sciences. My name is Peter Schad, I'm from the Technical University of Munich.
Hello, I'm Chris and I'm playing the student.
This is the WRB manual. Editor is the IUSS Working Group WRB. It's the 4th edition. Responsible are Peter Schad and Stefan Mantel, at that time chair and vice chair of the WRB Working Group. Published by the International Union of Soil Sciences in Vienna. Here is the link to the WRB homepage and the direct link to the WRB manual. The WRB is an open access document under the terms of the Creative Commons Attribution License. And I wrote an article explaining the WRB titled World Reference Base for Soil Resources, its 4th edition and its history, published in the Journal of Plant Nutrition and Soil Science in 2023. It's also an open access document. We are the only soil scientists on Earth who can do soil science barefoot. All others must wear shoes. So you must wear shoes. It's dangerous to do it barefoot. You must wear shoes. You got it? The risks in our region. A major risk are ticks, zoological name Ixodida. They transmit encephalitis, Lyme disease, also known as borreliosis, and other diseases. Against this type of encephalitis, there is a good vaccination. However, you need several shots for full protection. You always have to spray your feet and legs, even if not bare, with a repellent. A second major risk are open wounds. Tetanus bacteria may enter. There is also a good vaccination against that. Not in our region. We don't have snakes nor other poisonous animals. When you do field work, you do it at your own risk. We are not responsible for anything that may happen during your field work. Please note that you need adequate tools, clothing and shoes. Chris, did you use tick repellent?
No, not yet.
Oh, so you should do that.
Thank you. Do you want some as well?
Yes. And are you vaccinated against tetanus and against tick-borne encephalitis?
Yes, of course. How about you?
Yes, me too, of course. We are in southern Germany, ecozone of the temperate mid-latitudes. Mean annual temperature here is 8.2 degrees centigrade and mean annual precipitation 700 millimeters. It's a bit drier in late summer, but it's not really a dry season. And in the winter it's for snow. Climate is a soil-forming factor. Another soil-forming factor is topography. You see, we are here on a slope. A third soil-forming factor are the biota, the living organisms. This here is a forest. And according to the Central European plant sociology, this is a Gallio odoratifagetum. The dominant natural tree is beech, Fagus sylvatica, but it is a managed forest and we also have many spruce trees, Picea abies. Another soil-forming factor is the parent material. The parent material here is loess. Loess is an aeolian sediment, that means transported by wind. Wind, erosion and sedimentation happened several times here in Earth history. And the loess that we find here at the surface is from the end of the Würm glaciation. For wind erosion, we need a vegetation-poor environment. And this was the case at the end of the Würm glaciation. It was cold, it was dry. And the main source of the loess we have here are the pre-alpine valleys. So the rivers come from the Alps and they were wild rivers in that time, and there was a lot of sedimentation and erosion along the rivers. And this is the main source of the loess. Then it was driven to the east. We had westerly winds like we have them now. And the deposition is mainly on the plateaus and on the leeward side. So the leeward slopes to the east, like this one. How do we recognize loess? Two characteristics. First, the wind predominantly transports silt. WRB defines fine earth as soil constituents 2 millimeters and smaller. And the whole soil, this is all. Fine earth, coarse fragments, artifacts, cemented parts, dead plant residues, all of any size. And for the particle size classes, we use an isonorm. Coarse fragments are bigger than 2 millimeters, fine earth 2 millimeters and smaller, with 3 fractions. Sand 2000 micrometers to 63 micrometers, silt 63 micrometers to 2 micrometers, and clay 2 micrometers and smaller. Wind transports predominantly silt. Sand is too heavy. Fine sand may be over shorter distances, but sand is too heavy. And clay, the clay particles of course are lighter, but clay forms aggregates, and the aggregates are too heavy. So the wind transports predominantly silt. And Löss normally has carbonates, especially here. The rivers in the pre-alpine valleys, they pass through the northern limestone Alps. And there is always enough carbonate. So there is always carbonate in these aeolian sediments. What we have here at the surface is not necessarily the directly deposited löss. It may be reworked due to periglacial processes. We had permafrost soils here, cryosols, and the subsoil is permanently frozen and the topsoil thaws every summer. And then is waterlogged because the water of course cannot penetrate through the frozen subsoil. And then this soil, waterlogged, may move down above the frozen horizon. So we must be aware that what we see at the surface may be remodeled due to these periglacial processes. This profile is some years old, and with time many things can happen at the profile wall. Water flows down, takes soil material from the topsoil to the subsoil. Algae may grow, fungi may grow, mosses may grow. So before studying the profile wall, it's important to clean the profile. Chris, can you please clean the profile?
Okay.
No, not that way. So that's not enough. You need to use the spade, and you need to remove, let's say, 1 centimeter from the profile wall to make a nice vertical wall.
Okay.
So please use the spade. Is it easy?
Yeah, on the top it's easy, but I have the feeling that it becomes more difficult down here. But down here it becomes easy again.
Thank you, Chris. This looks good. Now the next task is to put the tape. Can you please place the tape?
Okay.
This is the tape, this is the stecky.
Where should I put it? Should it be right on the top or somewhere in between, or where is the zero line?
That's a good question.
Some important definitions in WRB. A litter layer fulfills 3 criteria.
It has more than 90% recognizable dead plant tissues. This is by volume and related to the fine earth plus all dead plant residues. And it is loose, and it is not connected to living plants, for instance, not connected to living sphagnum mosses. Soil organic carbon is organic carbon that does not meet the criteria of artifacts. Now we can define organic, mineral and organotechnic material. The first criterion is the percentage of soil organic carbon. This is by mass and related to the fine earth plus dead plant residues of any length and a diameter of 5 millimeters and smaller. So we include the finer roots and the moss fibers in our measurements. Organic material has 20% or more, mineral and organotechnic material less than 20%. None of them forms part of a litter layer. Now the percentage of organic artifacts by volume and related to the whole soil, this is for differentiating mineral and organotechnic material. Mineral has less than 35 and organotechnic material 35% or more. The surfaces. The soil surface, which is line 0 in WRB, this is directly below the litter layer and below a layer of living plants, if present. And the mineral soil surface, this is the upper limit of the uppermost layer consisting of mineral material. A soil layer is a zone in the soil approximately parallel to the soil surface, with properties different from layers above and or below it. If at least one of these properties is the result of soil-forming processes, the layer is called a soil horizon. In the following, the term layer is used to indicate the possibility that soil-forming processes did not occur, so using the term layer, we are on the safe side.
Yes, now it looks good. So we see the 0 line is directly at the soil surface.
Okay.
You see, this is the litter layer. It is loose and more than 90% of the volume consists of recognizable dead plant tissues. Now we have to measure it. The thickness may change. So here it's around 2 centimeters, a bit more, again a bit more. 2 centimeters, 2 centimeters. I think it's a good estimation to say that it has an average thickness of 2 centimeters. Maximum thickness may be 4. And look how much of the surface is covered by the litter layer. It's around 90%.
This is the soil description sheet, Chapter 11 or Annex 4 of the WRB. Part 1 consists of general data and description of soil-forming factors and the description of surface characteristics. These descriptions follow Chapter 8.2 and Chapter 8.3 of the WRB. The sheet starts with date of description, names of describing orders, location, landform and topography, climate and weather, and so on. This is the second part of the soil description sheet, description of layers according to Chapter 8.4 of the WRB. Chapter 8 is the field guide. Cells in brown require a code. For cells in green, a figure or a free text is needed. Don't leave cells empty. Write an A if a characteristic is not applicable and an I if you did not investigate it. In the headlines of the field guide, for every characteristic, an O or an M indicates whether it has to be reported for organic or mineral layers or both. The percentage is by exposed area, by volume, or by another criterion. This is always explicitly stated. Unless stated otherwise, the percentage refers to the fine earth and to the whole layer. So the whole layer, for example, if you have different substances of oxymorphic features, the 100% is not the part with the oxymorphic feature, but the whole layer. The sheet starts with the number of the layer, upper and lower boundaries, homogeneity of the layer, water, and so on. For this video, we prepared a short version of the soil description sheet, of both parts. We made invisible the columns of characteristics that cannot occur in our soil, and some additional columns because we did not want to do the description for this video in a too detailed way. This is the part of general data and surface characteristics. We have the date of description, names of describing authors, some details about location, landform and topography, and vegetation and land use, and then the litter layer. The area covered is 90%. The average thickness is 2 centimeters, the maximum thickness 4 centimeters, and there are no technical surface alterations.
The profile wall is not a good place to study the topsoil. The plant residues fall onto the soil, but some of them may fall into the profile. So the litter input here is reduced. That's why we need a topsoil clot. So we go somewhere close by the profile, but not directly here, and take a topsoil clot. Can you please do that, Chris?
Yes, of course.
No, don't walk here. This is the profile wall, and every year the profile wall will move a bit further back. So don't walk here, you are compacting the soil, and you can lose soil material, and then the soil surface here is contaminated with different soil material and you can't study the soil anymore. Don't walk here.
Okay, sorry.
And it's dangerous, you may fall into the profile.
We have three organic horizons, OI, OE and OA, differentiated by the state of decomposition, initial, intermediate or advanced. For the definition, the volume of recognizable dead plant tissues is used, related to the fine earth plus all dead plant residues. This is more than 2/3 for the OI, 2/3 or less but more than 1/6 for the OE, and 1/6 or less for the OA. The litter layer does not belong to the O horizons, but the litter layer has 3 criteria, and if one is not fulfilled, it is already an OI horizon. So there might be more than 90% recognizable dead plant tissues, and if this is compacted, this is already an OI horizon.
This is the mineral soil surface here. Further up we have organic horizons, further down mineral horizons. The plant residues fall onto the soil, animals come and take them into the mineral soil. Most effective are earthworms. If animal activity is somewhat reduced, these plant residues remain to a certain extent above the mineral soil. Bacteria and fungi decompose them there. So the residues fall onto the soil here, and further down they are more decomposed. So further down we have less recognizable dead plant tissues and more a homogeneous mass of microbially altered organic matter. And according to this gradient of decomposition we can distinguish the litter layer and up to 3 organic horizons, OI, OE and OA. What do we have here? We have the litter layer. We already measured its average thickness. More than 90% of the volume consists of recognizable dead plant tissues, and it is loose. And below the litter layer there is the soil surface here. And then we have around 3 centimeters of an OI horizon. I means decomposition initial. More than 2/3 of the volume consists of recognizable dead plant tissues. Here I would estimate it to 80%. And then we have around 1 centimeter of an OE horizon. E means decomposition intermediate. Between 2/3 and 1/6 of the volume consists of recognizable dead plant tissues. Here I would estimate them to 30%.
and there is no OA horizon. Animals are too active. Before this OA horizon can be formed, the organic substances are already mixed into the mineral soil. If we look at the lower horizon boundaries, the OI horizon, its lower boundary is clear and smooth, and from the OE horizon, this is the direct transition to the mineral soil. The lower boundary of the OE horizon is wavy and abrupt. This is the soil description sheet, layer descriptions. We have two organic horizons. The first is from 0 to 3 centimeters, the second from 3 to 4 centimeters. They both consist of organic material and are terrestrial. We have here the recognizable dead plant tissues. For the first horizon, they are estimated to 80%, which is an OI horizon. For the second horizon to 30%, which is an OE horizon. This is not applicable for mineral horizons.
Peter, what happened?
I have a thorn in my foot.
What? It pierced your thick callus?
No, not the callus, just here.
Okay, do you want me to remove it?
Yes, please.
Oh wow, that's a thick thorn.
Thank you.
You shouldn't walk barefoot, Peter.
You are right. You saw, at an undisturbed place, the combined thickness of our organic horizons is 4 centimeters. Here at the profile wall is less. Now I have to correct the tape. I have to put it in such a way that at 4 centimeters is the mineral soil surface. And now we start describing our mineral layers. So we apply the field guide, Annex 1, Chapter 8 of the WRB, and it has 5 subchapters. 8.1, Preparation Work and General Rules. 8.2, General Data and Description of Soil Forming Factors. We described some soil forming factors. 8.3, Description of Surface Characteristics. We described at least a little layer. And Chapter 8.4, Description of Layers. Now we have to find the limits between the horizons. What are the criteria how to differentiate horizons? There is, for instance, the color, then redox features, texture, coarse fragments, artifacts, bulk density, structure, carbonates, secondary gypsum, cementation, human alterations. All these are the criteria. So now I take my knife and I move it down, and Chris, can you please shout when you think that there is somewhere a horizon boundary, and tell me why you think that there is a boundary, what is changing. So okay. I start here at the mineral soil surface, 4 centimeters below the soil surface, and I move down.
Stop.
Here?
Yes, sir.
What changes here?
So it's slightly darker in the top and more bright below.
Yes. Okay. Then I continue.
Stop.
Maybe I was a bit already too far down.
Stop.
Yes. Around here, that's
yes.
Correct?
Yes.
Yeah, 48 centimeters. What changes here?
So there were 3 differences. First of all, the color changes. And then second, when I was cleaning the profile, I could feel that it was more dense below.
Yes.
And also the surface pattern, the structure should like somehow change.
That's correct. So we move further down.
Stop.
And what changes here?
It's again the color, and I have the feeling it looks more like the horizon to above.
Okay, thank you. These were the horizon boundaries. Now we measure them. The first horizon is from 4 centimeters to 16 centimeters. The second mineral horizon from 16 to 48 centimeters. The third mineral horizon from 48 to 85. And This one is the last one, the fourth mineral horizon, from 85 to 125. And for the last limit we say 125 plus, because we don't really know whether there is really a horizon boundary or not. We simply stopped digging. We now have the depths of the other horizons. The third horizon is from 4 to 16 centimeters, the fourth from 16 to 48, the fifth from 48 to 85, and the sixth from 85 to 125 centimeters. We call that 125 plus because we don't know whether this is really a horizon limit or it is just because we stopped here digging. None of these horizons consists of different parts, so the described parts is always 100%. And none of these horizons is composed of several strata of alluvial sediments or of several strata of tephra. We already called the first two horizons organic terrestrial, OT, and the other four are mineral. Let's have a look at the distinctness of the layer's lower boundary. How thick is the transition zone to the underlying layer? We have two columns. One is for mineral layers, organotechnic layers, and hydromorphic organic layers. So organic layers with a certain minimum time of water saturation. And the other column is for terrestrial organic layers. This is with smaller values. We distinguish very abrupt, clear, gradual, and diffuse. And now the shape. Smooth is more or less linear. Wavy is uneven with a smaller depth than width. Irregular with a larger depth than width. And the last option is broken. So let's have a look at the first mineral horizon at its lower boundary. Abrupt or very abrupt would be less than half a centimeter, the transition. Abrupt within 2 centimeters, clear within 5 centimeters. What do you think?
I think it's within 2 centimeters, so maybe abrupt.
Yes. And the shape, is it smooth? Is it wavy? Is it irregular?
I think it is wavy.
Yes, I think so too. Now let's have a look at this horizon boundary. It's at 48 centimeters. We have very abrupt, then clear is within 5 centimeters, gradual within 15, and diffuse more than 15 centimeters.
I think it's over maybe this size, which would be maybe 10 to 15 centimeters.
Yes, that would be gradual. And is it smooth or wavy or irregular?
I think it's smooth.
Yes, I think so too. Now this horizon boundary, is it very abrupt, clear, within half a centimeter, within 2 centimeters, within 5 centimeters?
I guess it's abrupt again.
Abrupt again. And is this smooth or wavy or irregular?
It looks quite smooth apart from a section in the middle.
Mm-hmm. So we have, of course, take this section into account, so it's wavy again.
Okay. Mm-hmm.
Okay. The last obviously has no lower boundary because we don't know where it is. Mm-hmm. We can now inform about the layer's lower boundaries. For the first horizon, which is organic, this is clear and smooth. The second horizon, also organic, abrupt and wavy. The third horizon, now we start with the mineral horizons, is abrupt and wavy. The fourth horizon, gradual and smooth. The fifth horizon, abrupt and wavy. And for the sixth horizon, this is not applicable. The total abundance of coarse fragments is 0, more or less, for all the horizons, and the total abundance of artifacts is also 0. For hand texturing, we use our ultimate soil texture flowchart. Hand texturing only provides an estimation of the texture. Especially around the limits between the classes, the results might be not absolutely reliable. The table shows the 12 texture classes with the required percentages of sand, silt and clay and some additional criteria. The 4 colors represent the 4 texture qualifiers of WRB: arenic, siltic, clayic and loamic. And at the right hand side you find the texture triangle,
At the bottom is the sand percentage from 0 to 100% using a brown color, and the percentage lines are from bottom right to top left. At the right hand side there is the silt percentage using a blue color from 0 to 100%, and the percentage lines are from top right to bottom left. And at the left hand side there is the clay percentage using a red saperavi color, and the percentage lines are horizontal. And this is the flowchart. The yes arrows are continuous and the no arrows are dashed, starting with a dot.
We now do the texture. We do it for the fourth, for the third and for the second mineral horizon, and we start with the fourth horizon. So the idea is take a sample of approximately 25 gram of bulk soil. Remove all coarse fragments.
Okay.
Are there coarse fragments?
No, I don't see any coarse fragments.
No. And remove all roots. Are there roots?
No, no roots.
Okay, so add water slowly and destroy all aggregates thoroughly. If the soil were kaolinitic, we had to take extra care to destroy pseudosand structure, but this soil is not kaolinitic. And the sample, except if very sandy, is at properest consistency when moldable.
Okay.
If the soil is too wet, we can add some more soil. If the soil is too dry, of course we can add some more water, but it seems that it's now in proper consistency. And now the next task is form a sphere with a diameter of approximately 3.5 centimeters by rolling the soil between both palms. No other technique, please. Roll it between your palms. Don't use the fingers. This would be another test. Can you easily roll a sphere?
Yes.
Let's see if it's around 3.5 centimeters. Yeah, it's a bit too
Roundabout.
big, but
I can remove
it's
a
okay.
bit.
The next task is squeeze the sphere between thumb and forefinger. Is it deformable with very low forces?
Yes, it's deformable.
Okay, if this is yes, the next task is place a piece of soil in your palm and drag the thumb of your other hand across it. Now the question is, does soil form flakes?
Yes, it forms flakes.
Beautiful flakes. And or feel flowery?
Also, yes.
Yes. The flowery feeling may also be described as a feeling of silt, or as a feeling of soapy or of silky. It's characteristic for silt. So we call it flowery, but you can also call it soapy or silky. Okay, and now the next question is, next task, squeeze the sphere between thumb and forefinger. And now three questions. Is soil shapeable?
Yes, the soil is shapeable.
Okay. And or adheres to the fingers?
What do you think? I don't think it's
No, it does
adhering.
not. And does it has grains to feel?
No, there are no grains.
Okay, but there are three questions, and if one is answered yes, then it's still yes, and with that we already have the result. It is siltlow.
The texture of the fourth mineral horizon is siltlow.
Okay, now clean your fingers please and take a sample of the third mineral horizon. Yes, again, remove all coarse fragments,
remove the roots, and then add water slowly and destroy all aggregates thoroughly.
Oh, that's much harder.
Yes.
Okay, I think there are no aggregates left.
No aggregates left, so form a sphere with a diameter of approximately 3.5 centimeters by rolling soil between both palms.
Yes, that works
Yes,
very well.
so can you easily roll a sphere? Yes. Next question, squeeze the sphere between thumb and forefinger. Is it deformable with very low forces?
No, it's deformable, but not with very low forces.
Okay, so this is no. And now the next task consists of two tasks. So the question is both of the following fulfilled? So first, squeeze the sphere with stronger forces until your fingers meet. Does soil cohere strongly and feel very plastic like plasticine or moist putty?
Have to try again.
Yeah, it seems it coheres.
Yeah.
And does it feel plastic?
Yes.
Plastic, yes. Okay, so the first question is answered yes. But it's an AND criterion, so let's have a look at the second question. Place a piece of soil in your palm and drag the thumb of your other hand across it. And now the question is, does soil take a polish?
I mean, I see some sparkling points, but it's not really a polish. It remains dull.
Yes, it remains dull. It's not the case that the whole surface takes a polish. Or does it feel smooth?
No.
No, not really. So the first question was answered yes, and the second was answered no. So this is in total no, because it's an AND criterion. And our next question is, does soil feel very gritty?
No, not gritty.
Not gritty. Next question, does soil form flakes and or feel floury and or remain well in fingernails?
So I don't have any flakes, but it feels very flowery, I have to say.
Does it remain in fingernails?
Yes.
Okay. So with that, it is silty clay loam. The texture of the third mineral horizon is silty clay loam. Now clean your fingers again and take something of the second mineral horizon. So remove coarse fragments, remove roots, and add water slowly.
This time we have some small roots.
Is it moldable?
Yes.
Yes, so form a sphere with a diameter of approximately 3.5 centimeters by rolling soil between both palms. Can you easily roll a sphere?
Yes.
And now squeeze the sphere between thumb and forefinger. Is it deformable with very low forces?
Yes, it's deformable.
Yes, it is. Now the next question. Place a piece of soil in your palm and drag the thumb of your other hand across it. Does soil form flakes and or feel floury?
Yes, it forms very nice flakes, and it is very flowery.
Okay, next question. Squeeze the sphere between thumb and forefinger. is soil shapeable and or adheres to the fingers and or has grains to feel? So is it shapeable?
Yes, it is shapeable.
Yes. And does it adhere to the fingers?
Yes, it does.
Yes, as well. And or does it have grains to feel?
No.
No, no. But if one of the three questions is answered yes, the overall answer is already yes. So this texture again is silt loam, and we know that the first horizon has the same texture, the first mineral horizon. This is also silt loam.
Okay.
The texture of the second mineral horizon is silt loam. We can now fill in the texture clause, which is only applicable for the mineral horizons. For the third and for the fourth horizon it is silt loam, for the fifth horizon silty clay loam, and for the sixth horizon silt loam again. Structure is the spatial arrangement of solid constituents and pores, and the solid constituents may be mineral or organic. An aggregate is a discrete structural body. Most types of soil structure consist of aggregates. In the granular structure, the aggregates are spheroidal, have many visible pores, and are bounded by curved or very irregular faces. In the subangular blocky structure, the aggregates are bounded by undulating rough faces, and many vertices are rounded. In the angular blocky structure, the aggregates are bounded by relatively flat, smooth, roughly equal faces, and most vertices are angular, and the massive structure is just a coherent mass. Now we detect the structure. We do it for all four mineral horizons, and we start with the lowermost horizon. Chris, can you please give me some specimens of the last horizon?
Yes, there you go.
Thank you. So if I apply forces to one of these, they just break where I apply the force. So they have no own will where to break. They have no natural surfaces of weakness. This structure we call a massive structure, and it is in this case inherited from the parent material, though it's a type of rock structure. So this is massive. We can think that it will after some time transform into a subangular blocky structure, but for the moment it's clearly a massive structure. Now the third mineral horizon, please. Yes, this looks very different, and you see this has natural surfaces of weakness. The soil has its own will where to break. And if you look at the vertices, they are sharp and angular, and if you look at the faces, they are more or less smooth and flat. This is what we would call an angular blocky structure. However, some of the structural elements have some characteristics of the subangular blocky, but mainly angular blocky. So you see here these sharp angular vertices, and the surfaces are smooth. Now the second mineral horizon, please. Thank you. Let's break them a bit, and you see this is what we call a subangular blocky structure. The vertices are rounded and the flats are undulating and uneven. And now the first horizon, please.
Here it was a bit tricky to get it out.
Yes, you already detected a problem. So this structure is very weak. So if you take it out, some of the aggregates are destroyed. And what we have here, these fine elements, this is the granular structure. So they are spheroidal, many visible pores, fluffy, curved faces. But we also have some elements that are subangular blocky. So these aggregates are subangular blocky with the rounded vertices and the undulating faces. But the dominant structure here, more the small aggregates, this is the granular structure. We can now fill in the structure. In the field we showed you the types, but here we will also give the abundance and the dominant size class according to our field guide. Structure is only applicable for mineral horizons. The third horizon has a granular structure in 60% of its volume with a dominant size class medium, and in 40% of its volume subangular blocky structure with a dominant size class also medium. The fourth horizon has subangular blocky structure in 100% of its volume with a dominant size class medium, and the fifth horizon in 80% of its volume angular blocky structure dominant size class coarse, and in 20% of its volume subangular blocky structure dominant size class medium. The last horizon has a massive structure inherited from the parent material in 100% of its volume, and size classes are not applicable if the structure is massive.
But Peter, here on the side of the profile we have a lot of cracks. Where do they come from?
Yes, that's an interesting observation. You see, we have these cracks only in the third mineral horizon, the one that has more clay and that had the angular blocky structure. And the reason for that is that we have swelling and shrinking clay minerals. So clay minerals that swell when they are moist and that shrink when they are dry. And when they are shrink, then these cracks develop. And this is quite typical for horizons that have a prismatic structure, not here, or an angular blocky structure. This is the color flow chart. We first have to ask, is the color a matrix color? If yes, then it's a matrix color. If not, our next question is the color the result of pedogenic processes? If no, we have lithogenic variegates. If yes, we have to ask, is the color the result of redox processes? If yes, we have redoxymorphic features. If not, we have non-redoxymorphic features. There are many non-redoxymorphic features. Now we will describe the matrix color. So Chris, can you please describe me the colors of these four horizons?
Of course. So this is maybe a brown, and this is another brown, and basically they are all brown.
Yes, but we have to do it in a more detailed way so that we can distinguish them.
Ah, okay. I see. Okay, so this might be coffee brown, and this is like ochre brown, and here we have a chocolate brown and another ochre brown.
Yes, I like coffee, I like chocolate, but this is not a way of a scientific description of the color. Color is always a bit individual. For that reason, some decades ago, Mr. Mansell developed the color charts. These are the color charts for soil. And the first thing to consider is the hue. The hue describes the colors that are used. So for soil, this is mostly a mixture of yellow and red. Yellow, Y, and red R. For instance, this is the hue 7.5YR. And we can do it yellower. So 10YR is yellower, 2.5Y is more yellow, and 5Y even more yellow. We can also go to the red side. So this again is hue 7.5YR. Then we have here 5YR, 2.5YR, and 10R, the reddest one. There are some other colors as well, some other hues. Now, for every hue, we have to consider two more characteristics. This is the value from 1 or 2 to 8. And you see a low value is a lot of black, and a high value is a lot of white. And then this one here is the chroma, from 1 to 8. A high chroma means a lot of color, and a low chroma means little color, just black and white. We will now detect the matrix color with a Mansell chart. If we start with the first mineral horizon, this one is very dark. So value and chroma are low, and it's very difficult to decide which hue this is. That's why I like to start with the lowermost horizon, and then I already have a U, and then I can see if this U continues for the first mineral horizon, for the one rich in organic matter. The color here in the field, we do it moist. Moist doesn't mean wet. Moist means moist. So we take a piece of soil, we spray it, wait until no water is visible, and then it is moist for detector color. So please start with the fourth mineral horizon, and we will see. Spray it with some water. So this here is U10YR, and let's see what fits. What do you think?
It might be this one here.
Yes.
It's value 5, chroma 6.
5, 6. But to be sure, let's check another.
Okay.
Let's check 7.5YR. Is this better or worse?
I think it's worse. It seems a bit too red.
Yes, it seems to be too red. So this is the fourth mineral horizon, 10YR 5, 6. Now the third mineral horizon, please. Let's wait until the visible water is gone. Now let's see. Do you have an idea?
I think we should try with a more reddish hue.
Redder one? Does this fit better?
Yes. Maybe this one here? What do you think?
Yes, this sounds good. So this is 7.5YR 4, 6. And now the second horizon.
Somewhere in between here, maybe like the first one that we had, but a bit not exactly. I think it's slightly more like slightly darker, so maybe it's a 4, 6, value 4, chroma 6.
Value 4, 6, it's better than 5, 6?
Yes.
Okay, so this is 10YR 4, 6. And now let's check the first horizon. What do you think?
Somewhere in between here and here. I would say either the 3-4 or the 3-3. The 3-3, I think.
I think so. So too. The 3-3 fits better. So this is 10YR 3-3. And when you are ready, don't forget to clean your Mansell charts. We did the matrix color, but you see here are some black spots. These are decaying roots, that's why they are so black. And then you see here, if you look very closely, some minor oxymorphic features, some masses or nodules. This tells us that this horizon, which in clay, exhibits a little bit of water stagnation, but it's very minor, so we ignore it. And finally, you see here some white spots. These are some stones, small stones. Loess normally doesn't have them, but below the loess here are sediments from the Neogene. they contain coarse fragments. And when there is a tree and it is thrown by wind, some of these small stones, some of these coarse fragments may come closer to the surface and mix into the loess.
We can now fill in the colors, which we only do for the mineral horizons. We have just one matrix color which accounts to 100% of the exposed area. For the third horizon this is 10YR33, for the fourth 10YR46, for the fifth 7.5YR46, and for the sixth 10YR56. We do not have lithogenic variegates, we do not have redoxymorphic features, at least not in a significant amount, and we also do not have initial weathering.
Now it's time to explain soil formation. We have here a clay poorer horizon and here a clay richer horizon. Why that? The reason is clay migration. So clay minerals migrate from this horizon to that horizon with the percolation water in the coarse pores. The question is now, why does that happen here and why doesn't it happen in all the soils? Clay minerals form aggregates. Aggregates are too big. They cannot be translocated in the coarse pores for the percolation water. We need dispersed clay minerals, single clay minerals, or at least very small aggregates. And now the question is, how are clay minerals dispersed? Clay minerals are negatively charged. So they absorb cations, and with the exception of those cations that are very close to the clay mineral, they all have a hydration shell. So water is a dipole and water is attracted, water molecules are dipoles, they are attracted by the cations and form a hydration shell. They are very strongly bound. And now it depends on the size of the hydration shell. If the size is small, then the clay minerals are close together and form an aggregate. If the size of the hydration shell is big, then they move away from each other. And the next question is, under which conditions these hydration shells are big and small. And this depends mainly on the valence of the cations. Divalent and trivalent cations have small hydration shells and monovalent cations have big ones. So Chris, can you tell me some monovalent cations?
Yes, sodium and
Yes.
potassium.
Yes, also the hydrogen and the aluminium dihydroxide. And these are the monovalent cations with the large hydration shells. And the question which cation is dominating, this is related to the pH value. If the pH is above 8.5, there is a dominance of sodium. Between 8.5 and 6.5, there is a dominance of calcium. And between 6.5 and 5, there we have some of these monovalent cations like potassium or aluminium dihydroxide. And if the pH value sinks below 5, we have a dominance of aluminium. Now, the parent material here is loess. So it has a lot of calcium carbonates. At the beginning, calcium is the dominating cation. And then the calcium carbonates are dissolved and step by step calcium ions are leached. And then we reach this pH range from 6.5 to 5, where we have some monovalent cations and some clay minerals move away from their aggregates and can move downwards. This is until the soil is more acidified, and then if we have the pH value of 5, aluminium is dominating, and this is the end of the clay migration. There is a direct proof of clay migration. Clay minerals are also called layer silicates. This is why they look like that, like a piece of paper. So the clay minerals move down in the coarse pores with the percolation water, but the water further down moves into the aggregates. in the medium-sized pores and the fine pores within the aggregates. The clay minerals can't follow them. They get attached to the surfaces of the aggregates, and there we can see them by two things. First, they have a shiny surface. We call these the clay coatings. So the clay minerals form coatings on the surfaces of the aggregates, and these coatings are shiny. This is due to the clay minerals themselves. They are layer silicates. But they also have a different color, not because of the clay minerals. Clay minerals are white or have a color that does not really contribute to the soil color, but clay minerals are associated with iron oxides. And what we see at the clay coatings is the color of the iron oxides, the intense color, the reddish color of the iron oxides. In some soils, even these clay minerals are associated with organic matter, so the clay coatings may also be darker.
We summarize our talk about clay migration. Clay migration means that dispersed clay minerals migrate downwards with the percolation water in the coarse pores. There is a chemical and a physical dispersion. The chemical dispersion depends on the size of the hydration shells of the adsorbed cations. Monovalent cations tend to have large hydration shells, and if some monovalent cations are present, clay minerals may be dispersed from their aggregates. But there is a second condition: low iron concentrations in the soil solution, so low salinity. If there are many ions, they compete with the adsorbed cations for the water, and adsorbed cations have small hydration shells, even if monovalent, and then we have stable aggregates. Physical dispersion: heavy rainfalls on a dry soil may flush off clay minerals from their aggregates. Stress features are the result of swelling and shrinking clay minerals. If in aggregates the clay minerals swell, the aggregate faces are pressed against each other and become shiny. This is what we call pressure faces. If in addition the aggregates slide past each other, sand grains in between may be moved and cause striations and grooves. Then we talk about slickensites. Different from that are clay coatings and bridges. They are the result of clay migration. Clay minerals, usually associated with iron oxides, move downwards with the percolation water in the coarse pores. The water is attracted by the medium-sized pores and fine pores inside the aggregates. But the clay minerals, being layer silicates, cannot follow and are attached to the surfaces of the aggregates and to the biopore walls. This is called clay coatings. If there are sand grains, clay may form clay bridges in between.
Now let's look for clay coatings. Chris, can you please pass me some aggregates of the third horizon?
Okay.
Thank you. Not too many at once. Yes. So you see, here are some clay coatings. They have a shiny surface. Color is not so different from the rest. Here the color is more different. So again, clay coatings. And if we remove the surface, you see the color underneath is a bit lighter. And let's see, here again we see the clay coatings, here not, but here they are. And they are shiny and have an intense color, and when removing them, the lighter color comes to the surface. Maybe one more. Thank you. Yes, here again we have clay coatings. You see the shiny surface, and it's also a more intense color than underneath, or compared, for instance, to this part here. If we estimate the surface of the aggregates covered by clay coatings, that's easily 50%.
Coatings and bridges are only applicable for mineral horizons. In the fifth horizon, we found that around 50% of the surfaces of the aggregates are covered by clay coatings, but no clay coatings in the other horizons. If the Munsell color value is 3 or less, we also have to look at the organic matter and oxide coatings of the sand and coarse silt grains. This color we only found in the first mineral horizon, and all the grains have intact organic matter and clay coatings. We prove the presence of carbonates with hydrochloric acid. Here is the reaction equation. Calcium carbonate plus hydrochloric acid form calcium chloride plus carbonic acid. The latter splits up into water and CO2 as a gas forms the bubbles. According to the effervescence with hydrochloric acid, we can distinguish the following carbonate contents: non-calcareous, slightly calcareous, moderately calcareous, strongly calcareous, and extremely calcareous. If we have secondary carbonates, they are differentiated by vision. We have masses, nodules and concretions, filaments, including the pseudomycelia, coatings on soil aggregate surfaces or biopore walls, and coatings on undersides of coarse fragments and of remnants of broken up cemented layers.
Löss contains carbonates. These carbonates are dissolved, and the highest chance to find carbonates is always in the lowermost horizon. So Chris, can you please take out some soil from the lowermost horizon? And I will add now hydrochloric acid. Yes, it bloaters, so it obviously contains carbonates. And now we have to check the abundance clause. Extremely calcareous, more than 25% by mass. This is described as extremely strong reaction. Thick foam forms quickly.
No, not really.
Not really. Let's read strongly calcareous, 10 to 25% by mass. Strong visible effervescence, bubbles form a low foam. Let's see. Yes,
Yeah.
that fits well, so it's strongly calcareous. So we were successful with the fourth horizon. Let's see now if the third horizon also has some carbonate. So I apply the acid.
Nothing.
We can't see anything, but if there's only very little carbonate, we can't see an effervescence, but we can hear it. So I add acid again, and please go there with your ear, and then you may listen if there is a reaction.
No.
No, so it's not calcareous.
Let's talk about carbonates. We found carbonates in the last horizon. It is strongly calcareous, but all the other horizons are non-calcareous, and we have no secondary carbonates at all.
We now do an estimation of the content of soil organic carbon according to Munsell value, Munsell chroma, and the texture. So we have here 4 columns. The left column is the Munsell value. Then we have 3 columns for soil organic carbon according to the texture class. And for our texture classes, silt loam and silted clay loam, it's always the column at the right. So Chris, can you please tell me a value and chroma, and I will tell you the organic carbon content.
So starting with the topmost horizon, we had a value of 3 and a chroma of 3.
Yes, this is soil organic carbon from 1% to 5%.
Then the second mineral horizon, we had a value of 4 and a chroma of 6.
So this is the line of the value of 4, but if the chroma is 6, we have to add half a value. So we have to check the line 4.5, and this is 0.2 to 0.5% organic carbon.
In the third mineral horizon, we also have the value of 4 and the chroma of 6.
So it's the same, 0.2 to 0.5% soil organic carbon.
And in the lowermost horizon, we have a value of 5 and a chroma of 6.
So value of 5, but if the chroma is 6, we have to take the value of 5.5. But this is the same result. Organic carbon content 0.2 to 0.5%. This is only a rough estimation, but we have to say why do we correct the value if we have a high chroma. High chroma means a lot of iron oxides. and they do not only give us an intense color, they give us also the impression that the color is a bit darker. So they pretend a higher content of organic matter, which we have to correct.
The estimation of soil organic carbon by color and texture is only possible for the mineral horizons. The estimation for horizon 3 is 1 to 5%, and for the other horizons 0.2 to 0.5%, and there is no black carbon at all.
We will now estimate the bulk density based on the packing density and the texture. For the packing density we have a simple method. We use a knife and see how this knife penetrates the soil. So if it goes in without applying forces, then the packing density is very loose. If we can put it in but with some forces, then it's loose. If it goes in only roughly half, packing density is intermediate. If only the knife point enters, then it is firm, and if it almost does not enter at all, then it is very firm. So Chris, can you please do this for all our mineral horizons? And it's always good to do it at least twice.
Okay, so on the very top I can push it easily in, but not like completely easy, but with a slight force, I would say.
Okay, this would be loose.
Then in the second mineral horizon I can push it maybe to half of the knife. Let me try again. Okay, yeah.
Yes, that's intermediate.
Then in the third mineral horizon, it's more dense, and I can, even if I apply higher forces, I can only push the
knife point.
Yeah.
Okay, so this would be firm.
And the last one, it's again like the second, so I can push it in halfway through. Okay.
Okay, yes, that's intermediate. Okay, thank you.
We estimate the bulk density based on the packing density and the texture. We obtained the packing density with our knife test and the texture with hand texturing. If the organic carbon content is high, the bulk density must be reduced by 0.03 kilogram per cubic decimeter for each 0.5% increment in organic carbon content. Now, our first mineral horizon, it has a packing density loose and the texture silt loam. This would give us a bulk density 1.15 to 1.6, but it has around 5% organic carbon. This is our lab result. So we must reduce this value by 0.3. This gives us a bulk density from 0.85 to 1.0 kilogram per cubic decimeter. The second and the fourth mineral horizon have the same values. The packing density is intermediate and the texture class is silt loam, leading to a bulk density from 1.35 to 1.8. And the third mineral horizon has the packing density firm and the texture salty clay loam. This gives us a bulk density from 1.45 to 1.75 kilogram per cubic decimeter. The bulk density is estimated for the mineral horizons. In the field we detect the packing density, and then we estimate the bulk density based on packing density, texture and organic carbon content. For the third horizon the packing density is loose, and the bulk density estimated from 0.85 to 1. For the fourth horizon, packing density is intermediate and bulk density estimated from 1.35 to 1.8. For the fifth horizon, the packing density is firm and the bulk density estimated from 1.45 to 1.75. And for the last horizon, the packing density is intermediate and the bulk density estimated from 1.35 to 1.8. For the horizons 4, 5 and 6, the bulk density is probably in the lower part of the indicated range.
We will now count the roots. We do it only for one example for the second mineral horizon, and we count the coarser roots bigger than 2 millimeters separately, and the fine roots 2 millimeters and smaller separately. We do it in a square of 1 square decimeter, and I will mark it here. So let's say here 10 centimeters, and then here 10 centimeters, like that. Okay, so please count here the roots, the fine roots and the coarse roots.
So we have 1 coarse root and 1, 2, 3, 4, 5 small roots, fine roots.
So the coarse roots, this is very few, and the fine roots, if it's just 5, this is also very few. 6 and more would be few.
Okay.
Let's talk about roots. We did not count the roots for the organic horizons, but for the mineral horizons. For the first mineral horizon, which is horizon 3, the abundance of fine roots is common, and of course roots very few. For the 4th horizon, both are very few. This is the one which we showed you. For the 5th horizon, the same, both very few, and in the 6th horizon there were no roots. Now the parent material. This is only applicable for the mineral horizons. Our parent material is loess in all the horizons, and this is indicated by the code UE1. The U stands for unconsolidated sediments, the E for aeolian sediments, and the 1, this is the dominant particle size class silt. We also have UE2, this is the dominant particle size class sand, mainly fine sand, but here it's silt, UE1.
We described many characteristics, but some characteristics we cannot describe here in the temperate mid-latitudes. So we have no secondary carbonates, secondary gypsum, secondary silica, no readily soluble salts, no permafrost features. In this soil there is also almost no redox features, so redox potential of course is high. We did not do the consistence, but the main characteristic of the consistence would be the cementation, which we don't have here. We don't have volcanic classes or endic characteristics here. We don't have human transported materials here. But now we can give the horizons a symbol.
We can now do the layer designations. Every layer receives a master symbol, which is a capital letter. Our soil needs the symbols O, A, E, B and C. In most layers, the master symbol is followed by 1 or more suffixes, which are lowercase letters. We use the Latin alphabet and some Greek letters.
We already have the OI and the OE horizon, the organic horizons, and this is the first mineral horizon. This is an AH horizon. The first mineral horizon is in many soils the A horizon, and here it's rich in humus, so it's a AH horizon. The alluvial horizon is the E horizon. The eluvial horizon is the BT horizon. Subsoil horizons are often called B horizons, and in this case it's BT. T is derived from the German word Ton, which means clay. And this is a C horizon, and it has primary carbonates, therefore it's a C alpha horizon.
We can now complete the horizon designations. We already had the organic horizons OI and OE, and we can now add the mineral horizons. The first one is an A horizon. It is rich in organic matter, therefore AH, followed by an E horizon. This is the alluvial horizon that lost clay minerals and oxides and maybe some organic matter. Then we have the BT horizon, the horizon that gained the clay minerals, the oxides and the organic matter. And the last one is the C alpha horizon. It is poorly weathered, therefore C, and it contains primary carbonates, which are indicated by the alpha.
What about the nutrients in this soil? There are some nutrients that are better available at a high pH value. These are calcium, magnesium and potassium. Parent material of this soil is loess, and especially in the subsoil we have a lot of calcium and also magnesium. We have also enough potassium, especially here in this clay-rich horizon. We have illites, and illites are clay minerals where we have in the interlayer fixed potassium ions. If they weather, the potassium is set free and plants can take it. Iron and manganese are better available at lower pH value, and these are available here in the topsoil. And we have to talk about nitrogen and phosphorus. They mainly depend on the mineralization of organic matter. Mineralization of organic matter, of course, releases all the nutrients, but for nitrogen and phosphorus, this is the major source. Well, for nitrogen we have to add that it also comes from the atmosphere. Now let's talk about the water. Plant available water capacity is high. This is because we have so many silt. Silt is the particle size that is associated with medium-sized pores, and in the medium-sized pores is the plant available water. In the coarse pores the water runs through the soil fast, and in the fine pores the plants cannot get it because it is held too strongly by the soil. But if we have medium-sized pores, this water is plant available, and we have a lot of medium-sized pores if the dominant particle size class is silt. Now the question, nutrients good, water good? Water good. We have no stagnant water, no groundwater, so no excess water, but enough plant available water. So nutrients good, water good. Why isn't there agriculture? This is because here is a slope. If here were agriculture, there would be a high risk of erosion, especially because of the silt. Silt is the particle size class where the risk of erosion is highest. Sand is a bit heavy to be transported by water when we think of water erosion, and clay is aggregated. The aggregates are heavy, and between the aggregates there are coarse pores, so water can infiltrate. Erosion, we always have water erosion if the water moves down at the surface, but if it's infiltrate, then like in a clay-rich soil, then there is no problem. But if it's silt, then it's a problem. Silt doesn't form aggregates, and silt is very light. So the risk of erosion is high, and this is probably the reason why here is no agriculture. For silviculture, we have a lot of silvicultural options. The dominant natural tree here is the beech, Fagus sylvatica, but we see there is also a lot of spruce planted, Picea abies. Spruce grows here very stable. Spruce is stable if it is possible that some deep roots are existing. This is the case here. Spruce doesn't like to do that if there is stagnant water, but here is no stagnant water, so the spruce trees, they have these deep roots that make the spruce stable. And the spruce needs water, it's still enough, but we don't know if this will be the case with climate change. The predictions are that we will have less rainfall, but even if the rainfall is the same, simply due to the fact that the temperatures are higher, we will have less water in the soil because higher temperatures mean higher evaporation. But for the moment it is good. Now we start with the second part, the classification according to WRB, 4th edition 2022. This is the WRB book. It has 13 chapters. Chapter 1, background and basics, just the introduction. Chapter 2, the rules for naming soils and creating legends for soil maps. You must read that. It's a very short chapter, but you must read that. If you don't read it, you will not be able to do a correct classification. Chapter 3, diagnostic horizons, diagnostic properties and diagnostic materials. Chapter 4, key to the reference soil groups with lists of principal and supplementary qualifiers. Chapter 5, definitions of the qualifiers. Chapter 6, Codes for the reference soil groups, qualifiers and specifiers. Chapter 7, the references. And now we have 6 annexes. Chapter 8 is Annex 1, the field guide. We just applied it. Chapter 9, Annex 2, summary of analytical procedures for soil characterization. This is just a summary. This is not a cookbook for the lab. Chapter 10 is Annex 3, horizon and layer designations. We just did it. Chapter 11, Annex 4, soil description sheet. We just filled it in. Chapter 12, Annex 5, guidance on database setup. And Chapter 13, Annex 6, color symbols for reference soil group maps. So for this classification of this soil, we have many criteria that are not related to the soil surface, but to the mineral soil surface. And to easily check the depth criteria, I now change the tape. I do it now in that way that the 0 line is here at the mineral soil surface.
Chapter 1 of the WRB provides the general rules. Here the general rules for the diagnostics. Diagnostics comprise diagnostic horizons, diagnostic properties and diagnostic materials. For the decision, only the diagnostic criteria are relevant. The diagnostic criteria must be fulfilled throughout the specified depth range unless stated otherwise. If a diagnostic horizon consists of several subhorizons, the diagnostic criteria, except thickness, must be fulfilled in every subhorizon separately. Averages are not calculated, unless stated otherwise. If a criterion is worded as a conditional clause and a condition, so the if clause, is not true, the criterion is ignored. Numerical values obtained in the field or in the lab have to be taken as such and must not be rounded when compared to the threshold values in the diagnostic criteria.
Now we have to check which diagnostic horizons we find in this profile. What are your suggestions, Chris?
We learned that we have some higher organic carbon content in the topmost horizon, so we might assume that there is a umbric or a molic horizon, but also in the same place it might be too thin for that. What do you think?
Yes, for umbric and molic, all the requirements will be fulfilled except the thickness.
Okay. And then this one here could be a cambic horizon.
Yes.
And the one with the clay eluviation could be an argic horizon.
Yes, let's check this one first. I will read the criteria and you tell me whether they are fulfilled or not.
Okay.
So an argic horizon consists of mineral material.
Yeah.
Yes, we have far less than 20% soil organic carbon. And first, has a texture class of loamy sand or finer.
Yes.
What was the texture class here?
It was silty clay loam.
Yes, so it's finer than loamy sand. And at least 8% clay. The lab data say that this horizon is 38% clay. And 2, one or both of the following, A or B. So if one is true, the whole criterion 2 is true, but it may be that both are fulfilled. So A has an overlying coarser textured layer. Yes, it has. With all of the following, now we have 6 criteria which are combined by an AND. So they must be fulfilled all. Only if they are fulfilled all, the 2A is fulfilled. So first, the coarser textured layer is not separated from the arctic horizon by a lithic discontinuity.
That's true.
That's true. And 2, if the coarser textured layer directly overlies the arctic horizon, yes, its lowermost sublayer does not form part of plough layer.
We don't have a plough layer.
We don't have a plough layer. And 3, if the coarser textured layer does not directly overlie the arctic horizon.
Which we don't have.
This is not true, so this if clause is not true. And if the if clause is not true, the criterion will be ignored. But let's read what it says. Then it says its lowermost sublayer, then it says the transitional horizon between the coarser textured layer and the Arctic horizon has a thickness of 15 centimeters or less. So that means the clay increase must happen at a very short distance. Now criterion 4, if the coarser textured layer has less than 15% clay, our lab data that this one has 19% clay, so this if clause is not true, the criterion is ignored. And 5, if the coarser textured layer has at least 15 and less than 50% clay. This is the case, it has 19% clay. Then the ratio of clay in the Arctic horizon to that of the coarser textured layer is at least 1.4.
Yeah, we have that.
Yeah, this is 38%, this is 19%, this is a factor 2, which is obviously more than a factor 1.4. And 6, if the coarser textured layer has at least 50% clay, this is not the case, so this criterion is ignored. Now, 2a is true, well, that 2 is true, and we are ready with 2, but we are curious soil scientists and we read what criterion 2b says, has evidence of alluvial clay in one or more of the following forms. First, clay bridges connecting at least 15% of the sand grains.
We don't find sand grains here.
Right. Or 2, clay coatings covering at least 15% of the surfaces of the soil aggregates, coarse fragments and or biopore walls. Is that the case?
I think if I remember correctly, you said that it was about 40%.
Yes, it was even about 50% the clay coatings, but this is more than 15% anyway. So, because these 4 criteria are combined by an or, if one criterion is fulfilled, the whole 2b is fulfilled, so now we are ready. And indeed we cannot check 2b3 and 2b4 because these are lab criteria and we don't have the results. But 2a is true and 2b is true, and 1 would have been sufficient. Now, criterion 3, both of the following. A, does not form part of a natric horizon.
We don't have an natric horizon.
No, there's no natric horizon, not so much sodium. And B, does not form part of a sporic horizon.
We also have
no, we don't have a sporic horizon, no acidic conditions with fossilization. But even if it were a sporic horizon, it could be at the same time an Arctic horizon if the alluvial clay, as evidenced by criterion 2b, is still visible. So in this case, there would be the soil formation, first an Arctic horizon formed, and then in that Arctic horizon, a sporic horizon formed. And if the criteria of clay alluviation are still fulfilled, if the clay alluviation is still visible, then it is both sporic and Arctic. And if the characteristics of clay alluviation have gone, then it's only sporic. But here it's not sporic. And criterion 4 has a thickness of 1/10 or more of the thickness of the overlying mineral material if present. We have overlying mineral material, and this has a thickness of 44 centimeters. 1/10 is 4.4. But our Arctic horizon, if it is Arctic, is from 44 to 81, so this is 37 centimeters. Much more. And one of the following, A or 2, A at least 7.5 centimeters if the Arctic horizon has a texture class of sandy loam or finer. It has, salty clay loam is finer, so this is the criteria that is relevant, at least 7.5 centimeters thickness. We have 37. But let's see what is criterion B. This is at least 15 centimeters. This is, it is really loamy sand, which is not the case here. And if the Arctic horizon is composed of lamellae, then these 7.5 and 15 centimeters refer to the combined thickness. So now we are happy, this is an Arctic horizon. And now let's check if this one is a cambic horizon. Again, I will read the criteria and you tell me what is fulfilled. A cambic horizon consists of mineral material. Yes. And has a texture class of, there are 2 options. So criterion 1 has a texture class of A, sandy loam or finer. Yes, we have silt loam. If it were sand or loamy sand, then it could still be fulfilled, this criterion, because criterion 1b says it's very fine sand or loamy very fine sand. But this is not our case is 1a. And 2, has soil aggregate structure in at least 50% by volume.
Yes.
It has soil aggregate structure almost in the whole volume.
Yeah.
And now criterion 3, this is the most difficult one, shows evidence of soil formation in one or more of the following. Now we have 4 options, A, B, C and D, combined by an OR. So if one is fulfilled, the whole 3 is fulfilled. But these criteria are a bit complicated. 3a, compared to the directly underlying layer not separated from the cambic horizon by a lithic discontinuity. Yes, this is the case. But this is the directly underlying layer. And the idea of criterion 3a is that the directly underlying layer represents the parent material of the cambic horizon. Which is not the case here. The parent material is represented here by the C alpha horizon. So we are a bit skeptical if this criterion would work out, but we will see. The idea is, when silicates weather, there is a formation of iron oxides and a formation of clay minerals. And the idea of this criterion 3a is we compare this horizon with the directly underlying layer and see if the color tells us that there are more iron oxides and if the texture tells us that there are more clay minerals. So criterion 3a has 3 subcriteria, 1, 2 and 3, and 3a1 refers to the U. Now, if the parent material is red, then due to new formation of iron oxides, it will be yellower, because what is created is mainly goethite, which makes it yellower. But if the color of the parent material is more yellowish, then the goethite makes it redder. And this is worded here. If the underlying layer has a mantle color U of 5YR or redder, then the cambic horizon has a U 2.5 units yellower. Okay, we have here 7.5 YR, so this is not 5 YR or redder, so the else case is ours, else a U 2.5 units redder. But this is not the case, the U is redder here, not there. So 3a1 is not true. 3a2, a mantle color chroma at least 1 unit higher. But they have the same chroma. But the idea is, again, we have new iron oxides, this make a higher chroma. And finally 3a3, a clay content at least 4% absolute higher. So the idea that here clay minerals have been formed. But we have another process, we have clay translocation, so we have here more clay than there. So 3a is not true. Now, let's have a look at 3b, compared to an overlying mineral layer, at least 5 centimeters thick, not separated from the cambic horizon by a lithic discontinuity. The idea is now we compare it not necessarily with the directly overlying layer, but with an overlying layer. But it must be mineral. And the idea is that this overlying mineral layer is rich in organic carbon and therefore has a dark color. And the cambic horizon therefore has a higher value. But it may also happen that this cambic horizon, in this cambic horizon, the iron oxides are better visible than in the dark horizon. And that's why this may have a redder U or a higher chroma. This we have, I think, more chances that this could be true.
Yeah.
Let's see. The overlying, we compare it with an overlying mineral horizon. This has to be at least 5 centimeters thick, so don't create a very narrow horizon, that's not the idea. And of course no lithic discontinuity in between. Now, one or more of the following. First, a mantle color U at least 2.5 units redder. No, that's not the case. Or a mantle color value at least 1 unit higher. Yes,
to remember.
it was,
Yes,
this is 3,
yes.
this is 4, this is 1 unit higher. Or a Mansell color chroma at least 1 unit higher. Yes,
Yeah.
it's even 3 units higher, from 3 to 6. So 3B is fulfilled. Now 3C, compared to the directly underlying layer. So we again compare it to this one, but the idea for the cambic is to compare it with that one. And criterion 3C deals with weathering of carbonates, dissolution of carbonates, removal of carbonates, also gypsum. So the idea is, in the formation of the cambic horizon, carbonates were dissolved, so here is a small amount of carbonates, or maybe none, and in the parent material there is still a high amount of carbonates. And this is a bit tricky to prove that. So compared to the directly underlying layer, not showing glacial properties. Yeah, this one has not glacial properties, but why is this important? Glacial properties means you have groundwater. The water moves upwards and it can take along calcium ions. And where the upward movement stops, calcium carbonate will precipitate, secondary calcium carbonate. And this is a completely different process, not suitable to prove a cambic horizon. That's why this must be excluded. And next criterion, this one, not forming part of a calcic or gypsic horizon. If you have a calcic or gypsic horizon, this is, we play in another league. This is not suitable to prove whether this is a cambic horizon. So this is also excluded. But here, no problem, this has not glacial properties, it's not a calcic horizon, not a gypsic horizon. And now we can see one or both of the following. 1, 5% absolute less calcium carbonate equivalent, or gypsum, than in this one, and no lithic discontinuity. If we compare calcium carbonate contents, then this is only possible if there is no lithic discontinuity. But this doesn't help us because there is no calcium carbonate in none of them. So criterion C1 is not true. Criterion C2, protocalcic properties or protogypsic properties in the underlying layer, but not in the cambic horizon. So the idea is here they were dissolved, the ions move downwards and precipitate here. And the nice thing of this one is that this may even be checked if there is a lithic discontinuity. So these are characteristics relevant for dry areas where we have these secondary carbonates and a lot of carbonates in general. So 3C is not true. Now let's have a look at 3D. Up to now we compared the possible cambic horizon with underlying or overlying layers. Now we have criterion that do not need this comparison. And the idea is, if there's a cambic horizon, there must have been a formation of iron oxides. And there are some lab criteria for that and some color criteria for that. So criterion D is all of the following, and now we have 3 possibilities or 3 criteria. They must be fulfilled all. D1, iron in dithionite at least 0.1%. So dithionite extracts all the iron in oxidized form. So this proves we have the formation of iron oxides. D2, a ratio between iron oxalate and iron in dithionite of at least 0.1. So iron oxalate extracts the poorly crystalline iron, so newly formed iron. So this tells us we have an active process of formation of a cambic horizon if we have this relationship. And we don't have the lab results, but for sure it has enough iron in dithionite and enough iron in oxalate so that D1 and D2 are true. And D3 we can check a Mansell color U of 2.5 YR to 2.5 Y. This is a wide range, but they all have iron oxides. And a chroma of more than 3. Yes, we have that. We have 10 YR46. So this is within the range of the YRs, range of the U, and chroma of 6, of course, is more than 3. So criterion D3 is also, criterion D3 is fulfilled, criterion D is fulfilled, criterion 3 is fulfilled. Now, criterion 4, and does not form part of the plow layer. No, we don't have that, and does not form part of. And now we have a list of horizons that are more advanced in soil formation or that are more specific in soil formation, and the idea is that then they are only, this horizon is only this diagnostic horizon and not in addition a cambic horizon. This is also true for layers with endic properties. This is also something specific, and it should not be at the same time cambic. This is the idea of criterion 4, and this is fulfilled, and criterion 5 has a thickness of at least 15 centimeters, and this is from 12 to 44, it has 32 centimeters. So this is a cambic horizon. Now we have 2 diagnostic horizons. The next question is, do we have diagnostic properties? What do you think?
That's a good question. So maybe like an abrupt textural difference?
Yes, so this means doubling of clay content or absolute 20% more. It doubles the clay content. This has 19, this has 38%, but it says abrupt.
Okay.
And we detected for this layer boundary that it is gradual.
Yeah, sure. And how about the retic properties?
Yeah, that's a good idea. We always have to think about retic properties if we have an archic horizon, but this means that the alluvial horizon interfingers with the archic horizon, which is not the case either.
Okay, yeah.
So we don't find diagnostic properties. Do we find diagnostic materials?
That's difficult. So could this here be cleric material?
This is also an important question. We always have to check that if we have an alluvial horizon, is it cleric material? But think of the chroma. Chroma is 6. This is too intense for cleric material. So there's no cleric material and therefore also no albic horizon.
But how about the calcaric? Because we found some carbonate.
Yes, so this we will read. The criterion for the calcaric material is quite easy. Calcaric material shows visible effervescence with 1 molar hydrochloric acid throughout the fine earth. Yes, it does. So now we have a cambic horizon, an archic horizon, and calcaric material, and now we can start with the key.
Okay.
Now we have to go to through the key to find the reference soil group.
But isn't it clear already? I mean, we found a cambic horizon, so that's why it's a cambisol.
Not so easy. First, we might find horizons that are more important than the cambic horizon, the archic for instance. And second, it still may happen that we overlooked something. So it's always better to go through the key.
Okay.
And the first soil in the key is the histosol. It has 3 criteria combined by an OR. So if one of these 3 criteria is true, then it's a histosol. But this soil is not a histosol. A histosol needs thick layers of organic material, and here our organic material is only 4 centimeters thick. And in the key we always have ready the principal qualifiers and the supplementary qualifiers. So we go through the key. The next is the anthrosols. Anthrosols have a long time of agricultural use and a significant enhancement of soil fertility, which is not the case here. Technosols, they have artifacts in one or another way. Cryosols, permafrost, no. Leptosols, there is continuous rock at shallow depth. No, we don't have that. Or alternatively, a lot of coarse fragments. We don't have that either. Soloniets have a natric horizon. We just said that we don't have one. Vertisols have a vertic horizon, so a lot of swelling and shrinking clays. Solonchak have salic horizon with readily soluble soils. Glasols, they have groundwater at shallow depth and clayic properties. No, we don't have that. Undersols mainly derived from volcanic ashes. No. Potsols, we already said that we don't have a sportic horizon. Plintosols, tropical soils with a plintic, pisoplintic or petroplintic horizon? No. Planosols and stagnosols, they have stagnant water and stagnic properties? No. Nitisols and feral soils are tropical soils. Then chernozems, castanozems, phusems and umbrisols need a chernic, molic or umbric horizon. Durisols, gypsysols, calcisols are for dry environments with a significant accumulation of secondary silica, secondary gypsum or secondary carbonates. Retisols, let's read that. Other soils having an arctic horizon starting within 100 centimeters from the mineral soil surface. Yes, it starts from the mineral soil surface at 44 centimeters. And having rhetic properties. No, we just decided that we have not. Next, acrisols, 3 criteria combined by an and. First, an arctic horizon starting within 100 centimeters from the mineral soil surface. Yes. And 2, a cation exchange capacity, pH 7, of less than 24 centimole charge per kilogram clay in some subhorizon of the arctic horizon within 150 centimeters of the mineral soil surface. No. Cation exchange capacity per kilogram clay here is high because we have 2:1 clay minerals. This is the criterion to identify kaolinitic soils. This is not the case. So no acrisol, but let's read the third criterion as well. Exchangeable aluminium is greater than the sum of exchangeable base cations, calcium, magnesium, potassium and sodium, in half or more of the depth range between 50 and 100 centimeters of the mineral soil surface, or if you have a limiting layer, then in the lower half of the mineral soil above a limiting layer starting within 100 centimeters from the mineral soil surface. And these exchangeable ions are always given in centimole charge per kilogram soil. And with that, it would mean that at greater depth we had a dominance of aluminium. This is not the case. We have a dominance of base cations. Next, lixisols. Again, they have an arctic horizon and again a low cation exchange capacity. Now they have a dominance of base cations, but because of the low cation exchange capacity, it cannot be a lixisol. Then the alisols, arctic horizon, now with high cation exchange capacity, but with the dominance of exchangeable aluminium, not the case. Now, Luvisols, other soils having an arctic horizon starting within 100 centimeters from the mineral soil surface. And now by default, this has a high cation exchange capacity and the dominance of the base cations, so this soil is a Luvisol.
WRB has 202 qualifiers. For every reference soil group, there is a shorter individual list of available qualifiers, subdivided into principal qualifiers and supplementary qualifiers. For classification, we have to check the lists from top to down and add all applying qualifiers. The principal qualifiers are ranked and listed according to their importance. They are added before the name of the reference soil group from right to left, so the first qualifier in the list is placed closest to the name of the reference soil group. Now, supplementary qualifiers. The list starts with the qualifiers related to texture, and if more than one applies in a certain soil, they are added from top to down the profile. Then all other qualifiers are listed in alphabetical order. Supplementary qualifiers are added after the name of the reference soil group in brackets and separated from each other by commas, from left to right. So also here the first qualifier in the list is placed closest to the name of the reference soil group.
Now we have to decide on the qualifiers. So we go through the list of the principal qualifiers. The first is abruptic. No, we don't have an abrupt textural difference. Then phreatic, we don't have a phreatic horizon. Petrocalcic, no petrocalcic horizon. Leptic, no continuous rock within 1 meter. Hydragric, anthragric, eragric, pratic, terric. These are the qualifiers for the anthropogenic horizons.
I have a question.
Yes.
Why are they separated?
With a slash?
Yeah.
This means that only one of them can apply. So, and there are two possibilities. Either they are mutually exclusive. A good example for that are the texture qualifiers. Arenic, clayc, loamic and siltic, they are mutually exclusive for this one horizon, of course. Or the second one is redundant to the first one, is included by the first one. We have here, for instance, dolomitic and calcaric. Dolomitic means dolomitic material. It has calcium carbonates and magnesium carbonates. Calcaric means it's calcaric material, it has calcium carbonate. So if it has calcium carbonate and magnesium carbonate, of course it has also calcium carbonate. So we don't add the calcaric, this would be redundant. We never add redundant qualifiers.
Okay.
So back to the qualifiers of the anthropogenic horizons, none of them applies. Gleic and stagnic, we have neither gleic nor stagnic properties. Vertic, we don't have a vertic horizon, which is strongly swallowing and shrinking clays. Rhodic and chromic refer to reddish colors, which you don't have here. Nudi Arctic would mean all the alluvial horizons are eroded and the soil surface, the mineral soil surface, is just here at the top of the Arctic horizon. This is not the case. Lamellic. The Arctic horizon consists of lamellae. No. Albic. We have an albic horizon above the Arctic horizon. No. Ferric. There's no ferric horizon. Gypsic and calcic. We don't have a gypsic or calcic horizon. Yamic and tachiric. Yamic properties, tachiric properties, these are desert features. We don't have them here. Scalatic, a lot of coarse fragments. No. Dolomitic, calcaric. Yes, we have calcaric material. So for the calcaric qualifier, it's not only needed that we have calcaric material, it's also a criterion that there is no calcic nor a petrocalcic horizon. If so, we have a calcic or the petrocalcic qualifier and not the calcaric qualifier in addition. But this is all fulfilled. We have calcaric material, we have no calcic nor petrocalcic horizon, but for the calcaric qualifier, the calcaric material must have a thickness of 30 centimeters at least within 1 meter. And this is not the case. Our calcaric material starts at 81 centimeters, so within 1 meter we have only 19 centimeters. Mm-hmm. But we will get back to that when discussing the supplementary qualifiers.
Okay.
So up till now we didn't find any principal qualifier, so the only one remaining is haplic. And haplic just says none of the previous qualifiers applies, and we use that the place of the principal qualifiers is not empty. Mm-hmm. So otherwise it would just be a Luvisol. Now it's a haplic Luvisol. We have at least one principal qualifier. This place is not empty. Many reference soil groups have this haplic qualifier, but not all. For instance, if you have a look at the next one, the cambisols, they don't have the haplic qualifier, because the list of the principal qualifiers of the cambisols ends with distric and eutric. Distric, dominance of exchangeable aluminium, eutric, dominance of exchangeable base cations. One must be dominant, so one of these two qualifiers always applies. Mm-hmm. That's why the cambisols and many others don't have the haplic qualifiers. But for the Luvisols, the dominance of the base cations is already part of the definition, so a eutric qualifier would be redundant and the district is not possible, so they have the haplic qualifier. Subqualifiers can be explained with an example. Loamic is the qualifier, amphi the specifier, and amphiloamic the subqualifier. There are two types of subqualifiers. Subqualifiers with a given definition, given in Chapter 5 of the WRB, and subqualifiers constructed by the user. The latter further divided into subqualifiers related to depth requirements. These are with the specifiers epi, endo, amphi, anno, catto, poly, panto, and bathy, and subqualifiers related to other requirements. Supplementary qualifiers are according to the alphabet, and this means according to the qualifier, not the specifier. If the specifier is proto, weakly expressed, bathy, great depth, or thapto, buried,
occur with principal qualifiers, the subqualifiers must shift to the supplementary qualifiers and are placed there according to the alphabet of the qualifier. Let's discuss subqualifiers related to depth requirements. The rules for constructing a depth-related subqualifier depend on what the qualifier refers to. 1. Qualifiers referring to a characteristic that occurs at a specific point of depth, for instance raptic. The epi, endo and amphi specifier apply. 2. Qualifiers referring to a layer, for instance the calcic qualifier referring to a calcic horizon, the arenic qualifier referring to a layer with sandy texture, the fluvic qualifier referring to a layer with fluvic material. The specifiers epi, endo, amphi, ano, cato, poly and panto are possible. 3. Qualifiers referring to the major part of a certain depth range or to half or more of a certain depth range. This is only district and eutric, and there only the specifiers epi and endo are possible. 4. Qualifiers referring to a specified depth range throughout. This is relocating only, and there only the epi specifier is possible. 5. Qualifiers referring to a percentage, for instance scalatic. The epi and the endo specifier are possible. Chapter 5 gives the definitions of the qualifiers, and if a subqualifier related to depth requirements can be constructed by the user, a figure indicates which rules apply. 1, 2, 3, 4, 5. And if no figure is indicated, these subqualifiers cannot be constructed. Examples: raptic is with rule 1, calcic is according to rule 2, and cutanic cannot have specifiers. There is no figure. Here is a figure explaining subqualifiers related to depth requirements and referring to a particular horizon or layer. Epi is within 50 centimeters. Endo is from 50 to 100 centimeters, but may even extend further down. Amphi starts above 50 centimeters, but not at the surface. It ends below 50 centimeters, but does not reach 100 centimeters. Ano starts at the surface, ends below 50 centimeters, but does not reach 100 centimeters. Cato starts above 50, but not at the surface, and ends at 100 centimeters or further down. Panto is from 0 to 100 centimeters, but may even extend further down. For every qualifier with depth requirements, the definition in Chapter 5 specifies whether the depth requirement refers to the soil surface or to the mineral soil surface. Subqualifiers related to depth requirements are only used if the relevant soil characteristics are reported until at least 100 centimeters or to a limiting layer. And now the polyspecifier. If referring to a diagnostic horizon, it may be used if a diagnostic horizon is present 2 or more times at the depth required by the qualifier definition, interrupted by layers that do not fulfill the criteria of the respective diagnostic horizon. If referring to other layers, poly may be used if 2 or more layers within 100 centimeters fulfill the criteria of the qualifier, interrupted by layers that do not fulfill the criteria of the qualifier, and the thickness criterion is fulfilled by the sum of the thicknesses of the layers. It may or may not be fulfilled by the single layers. And now a shortened explanation of the Bathy specifier. If the criteria of a qualifier are only fulfilled if layers at a depth of more than 100 centimeters are taken into account, the Bathy specifier can be used, and the Bathy subqualifier always extends to a greater depth than specified for the qualifier.
Now we have a look at the supplementary qualifiers. The first qualifiers are the texture qualifiers. We have silt loam from the mineral soil surface to 44 centimeters and again from 81 centimeters downwards. This is the siltic qualifier. And then we have siltic clay loam from 44 centimeters to 81 centimeters. This is the loamic qualifier. So now we have both.
But if both apply, then which one would come first?
Yes, that's a good question, and it has a good answer. Let's start with the loamic. We need the specifiers. Without specifiers, these texture qualifiers are not very meaningful. So this is amphiloamic. Amphi means it starts above 50 centimeters, but not at the mineral soil surface, somewhere in between. And it ends below 50 centimeters, but it does not reach 100 centimeters. This is exactly the case here, so it's amphiloamic. And siltic occurs twice, here and then interrupted and further down again. For this we have polysiltic. And the first one is always the one that starts at the mineral soil surface, or at least that is the uppermost one. So the sequence is polysiltic amphiloamic.
Okay.
Now, it's not endic, we don't have endic properties. It's not eric, we don't have a plow layer. Neocambic, this is also a question we have to ask. We have a cambic horizon from here to there, but it's not a neocambic. Neocambic is the following. We have primary silicates. When they weather, clay minerals and oxides are formed, and we have clay migration. To a certain extent, they migrate further down. But when the soil gets acidified, pH 5 or lower, dominance of aluminium, then this clay migration comes to an end, but the silicate weathering still goes on, or even faster, because now it's more acidic. And the clay minerals and the iron oxides newly formed, they stay where they are. So below the A horizon, in the upper part of the alluvial horizon, a new cambic horizon is formed. And this is the idea of the neocambic qualifier. In addition, it requires that in between the new cambic horizon and the archic horizon, there is at least some albic horizon, which we don't have either. So not neocambic, not columnic, we don't have a columnar structure. Now cutanic and differentic, these are the two criteria how we can prove an archic horizon. Cutanic refers to the clay coatings, we have that. Differentic refers to a difference in clay content, we have that as well. So we have both cutanic and differentic. In between, according to the alphabet, is the Danzig qualifier, but this is not Danzig. Next, epidistric and hypereutric. Epidistric means dominance of exchangeable aluminium in the topsoil. In the subsoil, we know there is dominance of base cations. This is part of the definition of the Luvisols. But in the top, it may be acidified, and there it may be distric. But I don't think that this is the case here. And the next is hypereutric. We know there's a dominance of base cations, and hypereutric means a strong dominance of base cations. Measured as centimole charge per kilogram, we have 4 times more base cations than aluminium. This is not the case. The next qualifiers, epic and endic, these are very important because they tell us at which depth the archic horizon starts. Epic means it starts at 50 centimeters or further up, and endic means it starts further down than 50 centimeters. So this is epic. Escalic, we don't have human-made terraces. Fluvic, we don't have fluvic material, visible sedimentation of fluviatile, lacustrine or marine origin. Fractic, we don't have a broken up cemented horizon. Gelic, we don't have permafrost. Humic and ocric. This refers to the weighted average of soil organic carbon. For humic, it is at least 1% the weighted average from the mineral soil surface to 50 centimeters, at least 1% soil organic carbon. This is the case here, I calculated it. And then we don't need ocric. Ocric would be redundant because ocric is at least 0.2% soil organic carbon in the first 10 centimeters.
Magnesic, more exchangeable magnesium than calcium. This is not the case. Natric, this would be a beginning of a podzolization. We would have uncoated sand and coarse silt grains in the A horizon, but we don't have that. Nitic, we have no nitic horizon. Novic, we don't have new sediments above the classified soil.
oxyarquic. This would mean a water saturation with oxygen-rich water, but we have no water saturation at all, neither with nor without oxygen. Profondic, this means that the Arctic horizon goes down to 150 centimeters. This is not the case, it only reaches 81 centimeters below the mineral soil surface. Pyric, black carbon, raptic, a lithic discontinuity within 100 centimeters, no. Sodic, high percentage of exchangeable sodium, we don't have that. Solomovic, this is solomovic material, a sedimentation caused by diffuse erosion, we don't have that. Technical-like, these are artifacts, we don't have them. Toxic, I strongly hope that this soil has no toxic substances. Transportic, this refers to human transported material, so humans transported natural soil from somewhere else to here, which is not the case. Turbic, we don't have cryotubation, neither recent nor relic, and vitric, we don't have vitric properties, so volcanic glass is a little bit weathered, so we don't have that. Now we are almost ready. But we are not ready because we said that we have to reconsider the calcaric qualifier. So you remember, it is fulfilled from 81 centimeters downwards, but for the calcaric qualifier it is required that we have 30 centimeters within 100 centimeters. This is not the case, but we do have the calcaric material over a thickness of 30 centimeters, even more, but at greater depth. And for this we have the bathy specifier, so this is bathycalcaric. It's calcaric, but not at the required depth, but further down. Now we have the soil name. It's a haploid Luvisol, polysiltic, amphilomic, bathycalcaric, cutanic, differentic, epic, humic.
Congratulations, you made it until the end. We want to thank you very much for watching our video, and we also want to advise you that you go into the field and do some soil science in the field yourself and find out about all the interesting aspects that you can find there.
Thank you also from my side. Hope you enjoyed the video, and I only can underline what Chris already said. Go to the field, take every chance to go on field excursions.